little bit of a case of the Wednesdays. Did you guys all grab one of the sheets? Yeah? Okay. All right, good. Well, that's a very good question. I'm sure the 8 a.m. part has something to do with it. I mean, I think he's just downstairs, so he'll be back in a minute. But as for where the other yokels are, well, they better be on Twitch or else unpleasant things will happen to them. So, yeah. All right. So, oh, yeah, the sheet thing. Oops. For today. Okay, so we're going to talk about limits at infinity today. And so let me switch the scene over to the Elgato so we can do our thing there. Okay, so we've talked about limits, one-sided limits, continuity. We've done a bunch of that sort of stuff, and there's sort of two issues that we need to dispense with, which is what happens when all the limits that we've dealt with thus far are x goes to a specific number, but what about if x is going to infinity or perhaps minus infinity? Okay, so that's one issue. And then the other issue would be what happens if we have like vertical asymptotes on a function, so a function's blowing up or something like that. How do we treat those things? Okay, and for those of you who are online, I have a new microphone. You can't really see it here in the room, but I look like I'm either giving a TED talk or doing a late night infomercial selling like cleaning product or something. Like, you'll be amazed at the power of this cleaning product. Huh? Yeah, ShamWow, or whatever. Yeah, actually, it came with a literally I am definitely selling cleaning product like headset thing, but I decided that was just too much, so I went with the lapel mic. Anyway, okay, so let's get to it. So let's start with the sheet. So if x is going to infinity, so what do we think this means? And maybe to sort of think intuitively, right, when we started with limits where x was approaching a number, we thought about sort of plugging in numbers that were getting closer and closer. So, like if x is going to 5, we did like 5.1 and 5.01 and something like that. So how could we sort of numerically experiment by getting close to infinity? Like, what is infinity? I mean, it's maybe a little too early in the day for that kind of deep. We need like granola, a bowl of granola and wine or something, and yeah. Yeah, really, really big numbers, okay? So if I put in 1 million and then 10 million and, really, really big numbers, what's 1 over a big number going to be? A really small number, okay? So accordingly then, what should we expect that this limit would be? If we get bigger and bigger on the x part, then the 1 over x's become smaller and smaller, okay? But they're still positive, right? 1 divided by a googolplex is still a positive number. It's just exceedingly teensy. Right, so what do we think? 0. Okay, that makes sense, right? Just from thinking it through. Okay, so that's 0, and the reasoning hopefully makes sense. Now, on the same token, if we can do it towards infinity, we can go the other direction towards minus infinity. And what's the answer going to this time going to be? Still 0, okay, but this time if we're approaching negative infinity, 1 over x, all the x values that we're plugging in are negatives, so it's approaching infinity from the underside rather than from the overside. Okay, does that make sense? And that sort of makes sense if we graph this thing. What does the graph of 1 over x look like? Do you guys remember? Okay, and then in the other, it's like that. Okay, so, and it has a horizontal asymptote here at x equals 0, and for that matter, it also has a vertical asymptote there at x equals 0. Okay, so good? Yeah. All right. Good. So now, obviously, we're here to do something a little bit more exotic than just 1 over x, and so right. Okay. So what about if we do stuff like, you know, a polynomial type thing? So in order to build up a polynomial, we need two basic pieces, right? What happens to constants as x is going to infinity? Yeah, the same thing that happens to them when you're going to any other number. There's no x's involved, so the limit of a constant is just itself. Okay, that's nothing new. And then this one is maybe kind of a silly question because, well, as x goes to infinity, what does x go to? Oh, I don't know, infinity maybe, right? So this would be infinite. Okay, now I want to be clear a little bit about the some of the lingo here. When I say this limit equals infinity, okay, that doesn't mean the same thing as if I'm saying that the limit equals 5. Reason, infinity is not a number. 5 is. Okay, so strictly speaking, the limit, if the limit comes out to be infinity or minus infinity, think of those as special cases of does not exist. Okay, but there are cases where we can be a bit more descriptive as to why the limit fails to exist. Okay, it fails to exist because it blows up towards infinity, as opposed to failing to exist because it just makes a squiggle motion forever or some other problem. Okay, so yeah, so it's a little bit of a like abusive notation to say equals infinity, but hey, I'm the one with the PhD, so I can do it. Yeah? Okay. There's only been one situation where I had to, like, literally arguing with, it was in a pretty advanced class, and I'm like, no, I know I'm right. I'm the one with the PhD. I can go upstairs and get it if I have to. And it was, I hate to play that trump card, but oh well. Okay, so let's look at two polynomials here, and we'll graph them. Oops, just for sake of demonstration. So okay, so let me just compare these two things. All right, so first off, which one of these is going to be bigger than the other for positive values of x? Yeah, clearly the first one, right? Because I've got plus 17x and the plus 39 will definitely do it, right? So the first one is definitely bigger than the second one. But what I want to sort of think about is what happens when the x's get really, 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 really big? Does the 17x or the 39 really matter much, so to speak? No. Okay, so if I graph these things, let me switch over to Mathematica here. All right, so get Mathematica open and go to full screen. Oh, sorry about the inception there. I don't want you. Okay, so pop open Mathematica, and then I'm just going to plot these two things together. So what was it? 2x squared plus 18x plus 39. So, whatever. Doesn't really matter, right? But that's okay. And 2x squared. So I'm going to plot these two things together on the same graph, and then we'll go from x from, say, 0 to 10 just to start, okay? And from 0 to 10, there's quite the difference between these two guys, right? I mean, they're both parabolas. One of them starts at y equals 39, right? That's the blue one, the first one. And then the orange one is the second one, which is just the 2x squared, okay? So nothing particularly exciting there. But if I start to go out to larger and larger x values, what happens? Yeah, they get closer and closer together. Okay, so this may be, it's something that when I first ran into it in high school, it kind of blew my mind for a few minutes. Who said that asymptotes have to be straight lines? Nobody, right? So what's happening here is that asymptotically, these two functions approach each other, right? So you can almost think of the orange one as being like the asymptote, and the blue one is approaching that asymptote. It gets as close as you want to it without ever actually touching. Okay, that's kind of interesting. And that will actually be relevant in CS stuff, right? Because like towards the end of last semester when we were talking about runtime, like big O notation, that sort of thing, right? Huh? Yeah, so I mean, that's the kind of thing you're dealing with. Nobody said that asymptotes have to be straight lines. Okay, good. So let's go back to the Elgato. All right, so the limit of these two things, they're both infinity, okay? But what we've seen is sort of how they get there, if you will. Okay, so now let's do next thing. I'm going to put a plus or minus there. Actually, let me, here. I wish I could do that on the chalkboard. Did you guys see what I just did? Yeah, so I can lasso something and just sort of drag it over. It'd be really cool if the chalkboards could do that. But get on that. I expect the new chalkboards to be installed by Monday. Yeah, okay. All right, so if, and I have to restrict this to n being a positive number, the reason being, what happens if n is negative and you've got a negative exponent? What does that do? Yeah, it flips it over. So if I've got a negative exponent in the denominator, that's going to flip the x back up into the numerator, and then I'd have x to a something in the numerator, which is going to go up to infinity, not 0. Okay. So this guy, the case of n equals 1, we've already dealt with, right? What was that? 0. Okay. Well, if I raise the x to a power of some sort, is that going to change whether or not this thing goes to 0? No, it just might change the rate at which it goes to 0, but it's still going to 0. Okay, so gone. Okay, so that is sort of our basic fact. And then what we want to do is think about situations like the following. Okay, all right, now, what does the top of this thing do? If x is going to infinity, what's the numerator do? Goes to infinity. What about the denominator? Also goes to infinity. So what's infinity divided by infinity? 1? Infinity? I don't know. Okay, so this is a situation that's kind of like the 0 over 0 thing. It's worse than does not exist. It's we don't know, okay, or what we call an indeterminate form. Now, as we will see after we work through it, in this particular case, the answer will be 1/2. Uh, and you might remember from high school, how did I just sort of know it's going to be a half, other than I'm the dude with the PhD? Yeah, the degrees are the same, and so then you look at the ratio of the leading coefficients, right? So that's a trick you guys probably learned in high school, and it's a perfectly good trick, right? And there's nothing wrong with it. Because, well, isn't it kind of nice to know what the answer is before you get started with the problem? Yeah, that's cool. But what we want to do is sort of prove or go through in nice and thorough why that actually works. Okay, because we're big boys and we're in big boy calculus now. Okay, so the trick with these is, what's the biggest power of x you see in the denominator for this particular thing? X squared, right? Yeah, there's a 2 in front, but I don't really care about that. Okay, so all I'm going to care about for right now is just the biggest power of x. Well, better late than never, huh? Same thing? Yeah. Well, I don't know. You don't want to get into a trash talking contest with McKinney. Yeah. I had lots of experience on the bus in elementary school to get some practice. Huh? Well, I mean, it was elementary school level trash talking, but yeah. Um, let's just say it didn't go over as well as I thought it would when I was like, oh yeah, well you're a piece of seborrheic dermatitis, which is the technical term for dandruff. Uh, yeah. Oh well. Uh, it'd be kind of like, imagine young Sheldon on the bus to school, right? All right. Anyway. Okay, so biggest power of x in the bottom is x squared. So what I'm going to do is I'm going to multiply the top and the bottom by 1 over x squared, okay? Now, the key here is it, in this particular example, the numerator also's biggest power was x squared, okay? So in this case, it wouldn't have mattered whose biggest power you picked. But always pick the one from the denominator. Just trust me, okay? The trick doesn't work otherwise. Okay, so now what we need to do is basically sort through the algebra. And before I do that, are we clear that by dividing and multiplying by the same thing, I'm not actually changing the expression I've got? I'm just going to change how it looks, right? Because all I'm technically doing is multiplying by 1, right? Okay, so let's distribute this through. So what do we get? I'm going to get, and let me be pedantic and just write this step out. For sake of demonstration. Okay, so that's what I did, right? And now let's simplify. So what simplifies here? Yeah, I get 1 plus 3 over x squared over 2 minus 5 over x squared. Okay? All right, so we're cool with the simplification? Yeah? Okay. All right, so next step. What's the limit of a fraction? I'm sorry? Oh, sorry, let me rephrase. That'd be like 1 over x or something. So just, but a generic fraction, limit of a fraction would be the fraction of the limits. Provided that, what's true? The bottom one can't be 0, okay? So I've got a limit of a fraction here. And so what I can do is say, all right, I'm going to take the limit of the top and then divide it by the limit of the bottom. Okay, then what's the limit? So on top and on bottom, we're taking the limit of a sum or difference of two things. So what's the limit of a sum? The sum of the limits. Okay, and what's the limit of a difference? The difference of the limits. Okay, so what we're doing here, right, is just obeying all of our limit laws. Okay, now the first two terms are just constants, right? So what's the limit of a constant? Yeah, just that constant. So we get a 1 here and a 2 there, and then some other stuff. Okay, well, what were the limits of the 3 over x squared and 5 over x squared? Those are both 0. That was sort of our basic starting fact. And so I've got plus 0 here and minus 0 there, which is just 1/2. Okay, now we knew it was going to be 1/2 because we knew the little trick about the leading coefficients, but this is sort of what proves it. Okay, and you guys are in big boy calculus, so you need to prove it. Okay, good. Question, Preguntas, Fragen? 9? Okay. So let's flip over to le dernier, or the page prochain. Okay. All right. So why don't we've got 3 more examples here. So let's just do. Why don't you do A? You do B. O, and you do C. A, B, C. Okay. Oh, you need one of the sheets, don't you? Sorry. Yep. And so just take a minute and work on that, and then we'll go through them together. While you guys are doing that, I am going to go grab a thing of water. I will be right back. What time did you go to bed last night? Why? That's a little late. That'll do it. That will do it. Yeah, I learned that the napping lesson my first year or two of college, that it doesn't work. Yeah, this is one reason why I, in the spring we typically put the Calc 1 section at 8 o'clock because it doesn't conflict with pretty much anything. And if there's only one section, we want to minimize the potential for conflicts. Right? There's not a whole lot going on at 8 in the morning besides, I don't know, constitutional law or something, right? So then on the other 2 days of the week, this is why I find myself volunteering to teach at 8, because I find that, yeah, getting up for an 8 a.m. class kind of sucks, but if you're doing it all 5 days of the week, it distributes the suck. And it's, not too bad to get into a routine. So, yeah, what are y'all's earliest classes on Tuesday, Thursday?
Tuesday it's 9:45. Thursday it's 2
Oh, that sounds rough. Yeah. You don't have any Tuesday, Thursday class? Oh. Yeah. So do you wake up or do you sleep in? That's not too bad. Right. All right, so what'd you guys get? Get the sheet so I know what I'm looking at here. What'd you get for A, the two of you that did A? 5? You got, okay. And that matches the leading coefficient trick, right? What about what's going on in B? What happens there? So here, what's true about the two powers? They're different, and who's bigger, the one at the top or the one on the bottom? The one on the bottom. Okay, so what does that one come out to be when all's said and done? What do you guys think it should be, those of you who didn't do that one? Guesses from the peanut gallery? Well, all right, what do you think? If it's a bigger exponent in the bottom, who's going to win in sort of the polynomial tug of war? Okay, and so it's going to go to 0. Okay, because the bottom gets so much bigger faster that you get 0. Okay, does that make sense? Yeah? All right, now you have to kind of go through all the limit stuff to show that that in fact happens, but it does. Okay, then what about C? What's happening there? Yes, and that's correct. Okay. Now C is has a little bit of a trick to it, right? Because what's x going to? Negative infinity, not infinity. Okay. If x had been going to infinity on part C, what would it have been? Infinity, not minus infinity. Okay. So the sign can matter, and that's sort of an example of that. Okay, Gucci? Yeah? So the rule of thumb, and A, B, and C all demonstrate this, is if you have a bigger power in the numerator, what happens? Okay, so this would be like example C. The numerator's bigger in power, what happens? The limit is? I'm sorry? Yes, it technically doesn't exist, but we can be a little bit more descriptive in this case. Okay, so remember here, x is either going to infinity or minus infinity. Okay, so, I mean, you're right, they don't exist as numbers, okay, but how can we be slightly more descriptive? They either go to, they either go to plus or perhaps minus infinity. Okay, if the top has a bigger exponent. All right, what about if the denominator has the bigger exponent? Then they go to 0 every time. Now, they might approach 0 from the underside or from the overside, and that depends on, minuses and pluses and stuff, okay? But it's still going to go to 0 in the limit, okay? And then what's the third case? The two exponents the leading exponents are equal, and what happened in that example? Yeah, okay, so we call those constants the leading coefficients. Okay, so the coefficient of the largest exponent is the leading coefficient of that polynomial. Okay, and so if we do that for the top and also for the bottom, then we have the ratio of the leading coefficients. Okay, so we're cool with the lingo? Yeah? Okay. What about online? We should theoretically have several people online, although I suspect that we still have several people in bed. Yeah, okay. All right, so flip over to the next page, and we got a little bit of a different situation there because all of the examples that we've worked thus far today were examples of rational functions. And let's just make sure that we remember the definition. What's the definition of a rational function? It's not a function that's majoring in philosophy. I'm sorry? Oh, I took your answer. Yeah, sorry. Okay, well, what's true about all the functions that we've examined up until this point? Fractions of what kind of things? Polynomials, right. So a rational function is a function that's a ratio, hence rational, of two polynomials. Okay? And the reason that we use that term for it is because, well, what's a rational number? Do you guys remember this? It's a ratio of two integers, okay, where obviously the bottom can't be 0. So 3/4 is rational, 5/7 is rational. Can you give me an example of a number which is not rational? Pi, square root of 2. Square root of 2 not being rational caused a bit of a kerfluffle in 2,500 years ago. Huh? Oh, because of this guy named Hippasus of Metapontum and the Pythagoreans. So the Pythagoreans were, well, to be honest, they were just as much, if not more so, a religious cult as they were a group of mathematicians. Okay, so and they had all kind of culty rules too, right? I mean, they did a lot of great math, right? We got Pythagoras' theorem out of it, right? But they also had a lot of weird rules. They were all vegetarians, which is kind of interesting. But, and I love this, they were forbidden to eat beans. Well, if you're a vegetarian, especially in 500 BC, cutting beans out of the potential diet doesn't really help your food supply, right? Because, yeah. Huh? Well, exactly, right? I mean, it's not like you had all the vegetarian, Beyond Burgers or whatever like you do nowadays, right? Which, actually, have you guys noticed that Sparks has been serving a lot of that stuff alongside regular meat? Hmm? Actually, I think that, like, the Beyond Burgers that they're doing on Monday, they're pretty good. Oh, that's... Yeah, well, I would too. Well, anyway, so there's a biography of Pythagoras written by another Greek named Iamblichus, much after Pythagoras' death, and he explains why they don't eat beans. Can you guys guess? Exactly. He literally says that, and to not eat beans, for they are flatulent. So, yeah. So that the beans, the musical fruit thing is really ancient in origin. So, anyway. Okay, so now, rational numbers, the square root of 2 being irrational, that posed sort of a big philosophical problem for the Pythagoreans, and there's variations on the story as to what happened to this dude Hippasus, that he was either the one who discovered it or communicated it outside the school, and then he was either burned at the stake, excommunicated, struck down by lightning, or sank at sea, right, depending on whose story you read. It wasn't a good day for Hippasus, though. Okay, so anyway. Right, so we don't have to do just rational functions here. We can do other stuff. So this first one would be okay, so one of the rules that we can use is, well, what happens if what is e to the x as a function? What property does it have? I mean, you guys know what it looks like graphically, right? Do you guys remember? No? Okay. I'll draw it. Huh? Well, yes, e to the x, but we don't know what a derivative is yet. So how can you talk about that? Okay, so its graph sort of looks like this, and this point is at 0, 1, and this point is at 1, comma, e. And what is e numerically, roughly? Yeah, 2.718, blah, 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 blah. Okay, it's kind of like pi in the sense that there's no pattern to the decimals after the decimal point, and it goes on forever. So anyway, that's what this thing looks like, but it so happens that it's a continuous function. And the fact it's continuous means I can do the following. I can say the limit of e is e to the limit of the thing. Okay, so that's a consequence of continuity, right? And so if I can figure out what the exponent does, then I just take e to that thing. All right, well, what's going on with this exponent? We got a polynomial. Okay, great. What does that polynomial go to? Goes to negative infinity. Good. You guys agree? All right, so I'm going to write the following in air quotes because it's not, I can't technically write this. Okay, and I can't write that because I'm treating infinity as if it's a number here, but it's not really a number. Okay, but what happens if I have e to a really, really, really small number? Okay, so negative. Well, look at the graph. Okay, so if I'm going towards, if x is going to infinity, then the exponent is actually going to minus infinity. So I'm actually going to the left on this graph. And what does that graph approach as x goes towards minus infinity? It goes to 0. Okay, do you guys remember that from high school? Yeah? No? Okay. Well, you know it now. So this is 0. Okay, and let's graph it just to kind of okay, so let me do, here's the graph of e to the x from, say, minus 2 to 2. Okay, so it's kind of like what I drew earlier. Okay, so that's just plain old e to the x. And just keep this in your brain. I find in Mathematica to do e to the x, it's easier to do exp of x, and that means do e to the x. Later in the semester, when I turn you guys loose on Mathematica, you'll just remember a few things. So, but we'll do that in spades later. Okay, so what would I actually care about here? Not e to the x, but rather e to the, what was it, 2 minus 4x minus 8x squared. Okay, and if I graph it, then what I get is kind of this bell curve looking thing. Okay, and in fact, this is, has anybody taken like a psych or a statistics class? Yeah, in high school? So the normal distribution, or the so-called bell curve, is basically e to the minus x squared. Okay, you adjust the constants, and what that does is tweaks what the mean and the standard deviation are. Okay, but this is basically the bell curve. And so as x goes to infinity or minus infinity, we're basically saying what happens if I go really far to the right, or in the particular one that we were looking at, really far to the left. What does it look like based on the graph? Yeah, 0 seems reasonable. Okay, and what we wrote on the sheet there is sort of demonstrating that yes, it is in fact 0, but the graph sort of makes our intuition work. Okay, so I guess what I'm trying to say partly is graphs are great, but they're just like anything else. They're a tool, right? And you can only do so much with one tool before you need a new, fancier tool. Okay. You know, if you've got a really awesome screwdriver, that's great until suddenly you need to change the tire on one of your on your car, change one of the tires. You need a different tool for that. And as you guys will discover when you get a little older and you buy houses, you suddenly have a need for a lot of really weird tools. And you begin your indentured servitude to Home Depot. So, or Lowe's if, yeah. Huh? Oh, yes, because you can save some big money there. Yeah. So I grew up in Texas mostly, and Menards doesn't exist down there. It's all Lowe's or Home Depot or Ace Hardware. And then I went to graduate school in Iowa, okay, where Menards most certainly does exist. And it was the weirdest thing going into Menards, because it's like a Home Depot, but the music, it's like sort of this weird combination of like Soviet propaganda, right? Because you've got that, that jingle about saving big money, right? Save big money, but they like make store music out of it. So in the back of your head, all you're hearing is save big money while you're getting bolts and lumber and stuff. I guess that must be what it's like going to North Korea, except you're not hungry also. So anyway, yeah. But yeah, you can get some good deals at Menards. And Home Depot will match their 11% things sometimes. So yeah. Anyway. Okay, let's throw some trig functions into the mix. So let me just go ahead and plot x squared sine x, which is the next one. And I'll graph it from negative 2 pi to 2 pi. Okay, so not surprisingly, it's going to be some sort of squiggly business going on. It's got a sign in it. Okay, but let's sort of decompose the two parts of this function, right? So what does sine x do graphically? Yeah, it just oscillates between -1 and 1 forever, right? What does x squared do? For small values of x, nothing particularly special, right? For big values of x, though, x squared gets really, really big, okay? So what this thing is going to look like if I go out to larger x values, and in fact, while I'm at it, let me throw sine of x, well, here, I'll do the original first, I'll do x squared second, and I'll do sine of x third, okay? So let me go out to like 10 pi in both directions. Okay, so what are the three pieces here? What's the orange dude? X squared. What's the green dude that you can barely see? It's sine of x. Now it looks like it's a horizontal straight line, but it isn't. It's just, because what does the graph of sine look like? It's just an oscillation. But what's the amplitude of that oscillation? How high does it get? 1 or -1 in the other direction. Okay, so the amplitude of it is 1. Well, what's the y scale of my graph here? Yeah, I've got, from -500 to 1,000 on here. So it is doing that oscillation thing, but the scale is such that we just can't see it. Okay, so what happens here is that the x squared guy kind of is an envelope for this thing. And so if x is going to infinity, then what do you think's happening to these wiggles? What's happening as I get larger and larger x's? Yeah, the amplitude of it gets bigger and bigger and bigger. Okay, so when I get all the way out there to infinity, what do you think is going to be happening? Yeah, it's going to be swinging between essentially plus infinity and minus infinity. Is that a specific number? No. So this limit as x goes to infinity does not exist. Okay, because it's not settling down on a specific number, nor is it only going to the positive infinities, nor is it only going to the minus ones. It's sort of bouncing back and forth. In fact, if I throw in one other graph here, we can kind of see why that makes sense. Okay, I can also throw in minus x squared, okay, which is now in red there. And you see how the blue, or the function of interest, is sort of bounded between those two parabolas. Okay, so that kind of makes sense? All right, so that's what happens if x is going to infinity with this one. But what about if I let x go to 0? What does the graph make us think is going to happen? It's going to go to 0, okay? But how could we prove that? Right, if we didn't have the graph, how would I prove it? Okay, so let me switch back over to the Elgato. Okay, so what I want to do is, so from the graph, our suspicion is that this is true. Okay, did that seem reasonable looking at the graph? Yeah? Okay, prove it. Squeeze theorem, big time, okay? And a good giveaway that a squeeze theorem situation is useful is when part of it is a trig function, particularly a sine or a cosine. Okay, so what do we have to do in order to apply the squeeze theorem? Right. So the first thing I need to do is get the function of interest squeezed between two other things. Okay, so I need to bound it. All right, now in this case, what's probably the bounds? I mean, the graph sort of gave it away. Yeah, okay, so maybe I should rephrase there. What is sine bounded by? Right, and therefore x squared sine of x is bounded by negative x squared and x squared, okay? So what I'm doing there is I'm saying, all right, well, I know for certain this is true, right, from trig class. And can I multiply everybody by x squared in that inequality? Yeah, totes. And do I have to flip any inequalities or do any of that nonsense? Not in this case. Why not? Right. You only have to flip the inequality if you're multiplying or dividing by a negative. But I multiply by x squared. That can never be negative. Okay, so I don't have to worry about that. Okay, so I do have now my function bounded between two other things. And what is true about these two limits? They're both 0, okay? And so what does that mean for our original thing? Yep. The squeeze got squoze, as we were discussing about the GameStop situation. Yeah, okay. So I'll let you guys look at C on your own. Similar idea, okay, but it's with cosine instead of sine. And so sort of think about how you could apply the squeeze theorem in that situation. Okay, then the last thing, and I'm afraid I kind of overdid it on time. We'll hit this at the beginning on Monday, just to make sure we're clear. How do we deal with vertical asymptotes? It's not that hard. Now I say Monday because what are we doing on Friday, gentlemen? Yes, your next assessment. So I look forward to your masterful demonstrations of mathematical prowess. Yeah, so we'll do that on Friday. So don't be late, or don't be in your bed, and we'll see you guys Friday.